Some of the most intriguing ideas come from Einstein's theories of special and general relativity. These theories suggest that with the right conditions in space-time or certain types of motion through space, time travel might be possible. Physicists have even discussed the concept of closed time-like curves. These are essentially loops in space-time that allow objects to return to their own past. Well, there are solutions in general relativity, like Gödel space-time, that describe such scenarios. But here's the kicker: the physical plausibility of these solutions is still up in the air. Now, when it comes to backward time travel, things get tricky. Many scientists believe it's highly unlikely. One big reason is causality, the idea that cause comes before effect. You've probably heard of the grandfather paradox. If you went back in time and accidentally prevented your grandparents from meeting, how would you ever be born to go back in time in the first place? Some physicists, like Novikov and Deutsch, have proposed ways to avoid these paradoxes using principles like the Novikov self-consistency principle or variations of the many worlds interpretation. So, is time travel to the past possible? As of now, it remains uncertain. But what about traveling to the future? General relativity suggests that traveling to the past could be possible in certain space-time geometries. These include concepts like cosmic strings, traversable wormholes, and the Alcubierre drive. These ideas hinge on the possibility of moving faster than the speed of light, creating pathways that loop back in time. But here's the twist. When we bring quantum mechanics into the picture, things get even more complex. One of the most intriguing aspects of quantum mechanics is how it deals with the fabric of reality at the smallest scales. Quantum effects could potentially alter the space-time geometry required for backward time travel. However, semi-classical gravity arguments suggest that when you incorporate quantum effects into general relativity, these loopholes might close. Enter Stephen Hawking and his chronology protection conjecture. Hawking proposed that the fundamental laws of nature might prevent time travel altogether. He suggested that once quantum effects are fully understood and integrated into a unified theory of quantum gravity, these exotic solutions allowing for time travel might vanish. But here's the catch. Physicists can't definitively say whether time travel is possible or impossible without a complete theory of quantum gravity. When we talk about quantum physics, one of the most intriguing concepts is the relationship between speed, light, and time. According to the theory of relativity, when a signal is sent from one location and received at another, as long as the signal moves at the speed of light or slower, all reference frames agree that the transmission happened before the reception. But what if the signal travels faster than light? In this hypothetical scenario, known as the tachyonic antitelephone, the signal would be received before it was sent in all reference frames. Essentially, it could be said to have moved backward in time. This mind-bending idea raises questions about the very nature of causality and time itself. Quantum mechanical phenomena such as quantum teleportation, the EPR paradox, or quantum entanglement add another layer of complexity. These phenomena might seem to offer mechanisms for faster-than-light communication or even time travel. In fact, some interpretations of quantum mechanics, like the Bohm interpretation, presume that information is exchanged instantaneously between particles to maintain their correlations. Einstein famously referred to this as spooky action at a distance. However, modern quantum field theories rigorously preserve causality, meaning they do not allow for time travel or faster-than-light communication. Detailed analyses of instances where FTL communication has been claimed have shown that classical communication must also be involved to transmit a signal. The no-communication theorem provides a general proof that quantum entanglement cannot be used to transmit information faster than classical signals. One such experiment is the delayed choice quantum eraser, conducted by physicist Marlon Scully. In this experiment, pairs of entangled photons are divided into signal photons and idler photons. The signal photons emerge from one of two locations, and their positions are measured in a manner similar to the double-slit experiment. Intriguingly, depending on how the idler photon is measured, the experimenter can either determine the location from which the signal photon emerged or erase that information. Although the signal photons can be measured before the choice is made about the idler photons, The choice appears to retroactively influence whether or not an interference pattern is observed when correlating the measurements of idler photons with the corresponding signal photons. However, since interference can only be observed after measuring the idler photons and correlating them with the signal photons, there is no way for experimenters to predict the outcome in advance, thereby preserving causality. Another thought-provoking experiment was conducted by Li Junwang. In this experiment, wave packets were sent through a bulb of cesium gas, making it appear as though the packets exited the bulb 62 nanoseconds before entering. However, a wave packet is not a single, well-defined object. It is a sum of multiple waves of different frequencies. This effect can make the wave packet appear to move faster than light or even backward in time, but it cannot be used to send any matter, energy, or information faster than light. Thus, this experiment does not violate causality either. Physicists Gunther Nimtz and Alfons Stahlhofen from the University of Koblenz claim to have violated Einstein's theory of relativity by transmitting photons faster than the speed of light through a phenomenon known as quantum tunneling. In their experiment, microwave photons traveled instantaneously between a pair of prisms moved up to 3 feet apart. Nimtz described this as the only known violation of special relativity. However, other physicists argue that this phenomenon does not allow information to be transmitted faster than light. Quantum optics expert Ephraim M. Steinberg uses the analogy of a train traveling from Chicago to New York, dropping off train cars at each station. In this way, the center of the train moves forward faster than any individual car, but no single car exceeds the speed limit. In a peer-reviewed journal, Shengwang Du claimed to have observed single photons precursors, stating that they travel no faster than the speed of light in a vacuum. His experiment involved slowing light through rubidium atoms and passing it through a vacuum. Both times the precursors preceded the photon's main bodies, traveling at the speed of light in a vacuum. According to Du, this implies that there is no possibility of light traveling faster than the speed of light, and thus no possibility of violating causality. If time travel is possible, then where are the time travelers from the future? Many have argued that the absence of time travelers from the future demonstrates that such technology will never be developed, suggesting that it is impossible. This notion is analogous to the Fermi paradox, which questions the absence of evidence for extraterrestrial life despite the vastness of the universe. Just as the absence of extraterrestrial visitors does not categorically prove they do not exist, the absence of time travelers fails to prove that time travel is physically impossible. It might be that time travel is possible but is never developed, or perhaps it is used so cautiously that we are unaware of it. The renowned astrophysicist Carl Sagan once suggested the possibility that time travelers could be among us but are disguising their existence or are not recognized as time travelers. Some theories of general relativity propose that time travel might only be feasible within a region of space-time that is sufficiently warped. Consequently, time travelers would be unable to journey back to periods before this region existed. Stephen Hawking proposed that this could explain why the world has not already been inundated by tourists from the future. Several intriguing experiments have attempted to entice future humans who might invent time travel technology to visit the present. Events such as Perth's Destination Day and MIT's Time Traveler Convention publicized permanent advertisements of a meeting time and place for future time travelers to attend. In 1982, a group in Baltimore, Maryland, calling themselves the Chrononauts, hosted an event welcoming visitors from the future. These experiments could have generated a positive result demonstrating the existence of time travel, but so far no time travelers are known to have attended any of these events. Some interpretations of the many worlds theory suggest that future humans might have traveled back in time but arrived in a parallel universe, thus explaining their absence in our timeline. As we ponder these enigmatic possibilities, we are reminded that the nature of time and reality is still a profound mystery. What do you think? Could time travelers be among us, unseen and undetected, or is time travel an insurmountable dream? Share your thoughts in the comments below.